So far the ionic compounds that we've talked about have involved metals that have been in only a certain region of the periodic table. All right, we've used metals that are in the first two groups, that would be the alkali metals and the alkaline earth metals. We've also talked about aluminum here. All right, but so far we have not talked about any ionic compounds that have metals from the transition metal region of the periodic table. And one of the reasons for that is they become a lot more complicated in terms of naming. When trying to predict the formulas of compounds that had alkali metals, it was very straightforward because the charge on the cations that those metals make is always the same. All right, it's always +1. All right, same thing for the next group. All right, all of the charges for the alkaline earth metals are +2. All right, and then if you consider aluminum being right next here to magnesium, it's +3. But notice that the common charges on the ions in the transition metal region are very varied. All right, and so this makes determining the formulas of these compounds a little bit more complicated. So one thing that's different about metals that are in the transition metal region of the periodic table is that you can't tell the charge on their atom by the periodic table position. We'll use silver as an example. Whereas before we could say that everything in this column was +1 and everything here was +2, well, silver is way over here. All right, there's nothing about this particular position on the periodic table that would give away that the ion that it tends to make has got a +1 charge. The other thing about them is that they are capable of making multiple different ions. All right, so in contrast, let's consider sodium, which is not a transition metal. All right, we know that sodium, because of the octet rule, only ever wants to lose one electron when it makes an ion. All right, and that's why we only ever get Na+. There is no such thing as Na+2. All right, because that just would not happen according to the octet rule. All right, but when we're talking about the types of ions that transition metals can make, we'll take copper for example. Copper sometimes can lose just one electron to make a copper +1 ion. All right, sometimes it can make a copper +2 ion. All right, but it never will lose 3 electrons to make a copper +3 ion. All right, so both of these ions are possible. All right, iron, for example. All right, it never just loses one electron. All right, it can only exist in the +2 or the +3 state. All right, and both of these are possible. So this creates a little bit of a difficulty when doing formulas for compounds containing these ions. All right, because there's more than one charge present, whereas when we were dealing with the other metals, there was only one charge that was possible. And this creates a problem when coming up with formulas of compounds. All right, so we just said above that both copper +1 and copper +2 ions exist. All right, so if that's true, we should be able to make an ionic compound by combining this ion with the chloride ion. And if we did that, we applied the crisscross rule, we would get a formula which is CuCl. But if we did the same thing with the other type of ion that copper can make, we should be able to crisscross those and we would get CuCl2. Okay. And it's important to note that these are two entirely different compounds. All right, even though they are both ionic compounds comprised of copper ions and chloride ions, this one right here, CuCl, looks like this right here. It's a pale green solid, all right, and it has its own melting point and its own set of physical properties. All right. The other compound has a much deeper green color and is much more soluble. All right, so it's not just a trivial difference between the two types of. These are two different compounds, just like sodium chloride would be different from potassium chloride, for example. All right, so a problem arises whenever we have to give names to these compounds, because if we followed the same rules that we did for ionic compounds, remember we just used the name of the first of the metal, and then the "-ide version of the nonmetal. All right, and with ionic compounds, we did not include the prefixes. There are no such things as monos, dis, tris in this. So if we were just to say copper chloride, we wouldn't be able to distinguish between these two compounds. All right. So, and remember, that's a common theme. For if you have a name, you should be able to tell exactly what that formula is from the name. All right. So the way that we get around this with these what are called transition metal compounds, or sometimes they're called, excuse me, sometimes they're called multiple charge cations. A name that I use for them is switch hitters. It's a reference to baseball, where sometimes a batter could bat left-handed or right-handed, in the same way that these ions could either have this charge or that charge. The way that we deal with this is we include a Roman numeral as essentially like a middle initial in the name. All right, so both of the compounds would be copper chloride, but this one right here has a Roman numeral 1 in the middle, and this one right here is going to have a Roman numeral 2. And what that Roman numeral represents is the charge on the metal cation. All right, so this Roman numeral 2 says that this copper chloride is the variety where copper has the +2 charge, whereas this copper chloride is the variety where the copper has the +1 charge. And if you track this back, you can see that that is the ion from which these compounds right here derive. All right, so if you're not familiar with Roman numerals, it's fine if you just learn through Roman numeral 6. You will not need to know any higher than that, and these are what those would be. So first we're going to go through how to go from a name of a compound having one of these transition metal ions in it to a formula. All right, and so let's start off with this name right here, manganese, and the way you would pronounce this is manganese 2 sulfide. All right, so the way that we're going to go about this is we're going to take advantage of something that we already know. All right, we already know what the charge is on the ion of a sulfide ion. All right, and we do that just by doing what we did before. Recall that sulfide is the ion of sulfur, and it's in this column, and everything here has got a -2 charge. So we know that sulfide is going to have a -2 charge. But as far as manganese, manganese is right here. And notice that manganese comes in two varieties. It comes in a +2 and a +4 variety. So how do we know which one of those we're talking about? That's what the Roman numeral does. It tells us that this is the manganese variety that has the +2 charge. All right. So if we write down both of these ions and simply apply the crisscross rule, we would get Mn2S2, and then you just do what we've done before. We simplify, we simplify these to the simplest ratio, which would be a 1-to-1 ratio between those. So we also need to be able to go from formulas of compounds that have these transition metal ions back to names. All right. So I'm going to give two examples of this, and there's different methods for how to do this. This is what I think is a fairly straightforward, simple way of thinking about this. So if we look at this formula right here, right? This is a compound. We have to first ask ourselves, is this one of those ionic compounds that requires a Roman numeral, or is it not? All right. And the way to determine that is to look and see, is it a transition metal? All right. And if it's a transition metal, for most of these, we're going to need a Roman numeral. So if you look at iron's position on the periodic table, notice that it's in the center section of the periodic table. All right. So from that, you can assume with these three exceptions I'm going to give you that it's going to need Roman numerals. All right. The only three compounds that are transition metals that don't need Roman numerals, and then you're just going to have to memorize these charges, are silver, cadmium, and zinc. All right. So silver's got a +1, cadmium has got a +2, zinc has got a +2. whenever you have compounds, those compounds, they do not need Roman numerals because they only have one, they only come in one charge. But iron is a compound that does need it because it exists as, it can come in two different varieties. It comes as a +2 and a +3 variety. All right, so how are we going to figure out which one of these we're going to need? So first of all, what's something about its name that we already know? All right, we know that its first name is going to be iron. All right, that's just the name of the first atom. And then we know that the last name is going to be oxide, because that's the "ide" version of this element right here. All right, and we also know that it's going to require a Roman numeral. And I've covered that up for right now. And this is the method for figuring out, well, what is the charge on this particular atom? Like, are these two iron atoms, are they the +2 variety or are they the +3 variety? All right, so we take advantage of something that's true about all ionic compounds, is that if you added up all the charges of all the atoms in the formula, it's going to be overall neutral. All right, that's not because they're neutral atoms. The oxides are negatively charged and the iron atoms are positively charged, but overall those charges are going to balance each other out. So here's the way I describe this is to kind of use a seesaw. All right, let me move this guy up a little bit. All right, and so hopefully you can see, I've just kind of drawn a teeter-totter here, where what's on the right side is going to be all of your negative charge, which come from those ions, and what's on the right side is going to be the positive charge. And because this is overall neutral, you're going to have the same amount of negative charge as positive charge. All right, so let's start with what we know. All right, we know that there are 3 oxide ions in this. All right, so what I've just done there is I've just drawn 3 of those oxygen atoms, and we know, based on oxygen's position, we know that oxygen comes as a -2 charged ion. So if there are 3 of these things and each one has a -2 charge, we could calculate what the overall amount of negative charge is. That would be a total of -6. But we know that the overall compound is neutral. So how can it be neutral if we've got a -6 charge somewhere in this? Well, we know that that means that somewhere there's got to be a +6 charge to balance that out. So we know that somewhere in this there's a +6 charge, all right, or a total of +6. And where is that +6 coming from? It's coming from these 2 iron atoms. So we know that 2 of the iron atoms have to somehow come up to make +6 charge, all right? And the way that that's going to do that, and I use the analogy of this is the bill, and then the bill is going to be split by however many atoms are there. All right, so if your bill is 6 and there's 2 atoms to split that, that means that each has got to come up with +3 charge. And what that Roman numeral is, remember, is the charge, excuse me, the charge on the metal ions. So since this charge is +3, that means that your Roman numeral is going to be 3. All right, let's try that one more time with this compound right here. Again, we start off knowing that it's iron sulfide. All right, we know that it needs a Roman numeral because it's iron, which is a transition metal. And so how do we figure out that charge? Well, let's start off with what we know. All right, the negative ion. It's a monatomic ion. It's just sulfide, which we know from its position is -2. All right, in this case, there's only one of those. All right, so what's the total charge from one ion having a -2 charge? That would be a -2 total. So therefore, that's got to be balanced by a +2. All right, and if you look at the formula, can iron, does this atom right here, can it split the bill or does it have to pay the whole bill? Well, if there's only one atom that's got to come up with that total, it has to come up with the entire charge that's required. If there were 2 atoms here, they could split that and they would each be +1. All right, so again, that charge right there determines the Roman numeral. So that would be iron 2 sulfide.